All right, in this video lecture, I'm going to cover 6.5 Part 2, Intermolecular Forces, which means that we are looking at forces between molecules. All of the bonds that we've discussed today are in this chapter: ionic, covalent, nonpolar, covalent, metallic. Those are intra because they are found within the molecules, and these interactions happen outside of the molecules. So these types of forces are generally weaker, okay, than our intramolecular bonds. And a good indicator of the strength of these intermolecular forces is looking at the boiling point. And if you see something that has an extremely high boiling point, then they must have a strong intermolecular force at work. And just a note, ionic compounds in your metals tend to have the highest. So ionic bonds, those are the strongest, followed by metals, and then you have to look at polarity. So it'd be your hydrogen bonds, dipole, and then your weakest would be your London dispersions, which deals with nonpolar. So I'm going to go through the four types of intermolecular forces here. Here's a table just showing melting points, and you can see that the ones that have high values, you can probably guess that they have strong intermolecular forces at work. Covalent substances, things that tend to be nonpolar, low melting points and boiling points. Okay, so I'm going to go through four types. Dipole is the first one, and it deals with polar molecules. And basically, what happens is that we have polarity going on, and where one half is negative, the other half is positive, and they act like tiny little magnets towards other molecules. And so that's an interaction. So we call it a dipole-dipole force. So this acts on very short ranges, and it can explain the differences between boiling points of various compounds. So I'm going to draw water here. And I already know what water looks like. It's a bent molecule, 2 hydrogens, 2 lone pairs. Now, oxygen has a high electronegativity value compared to hydrogen. And so I think oxygen's like 3.5 and hydrogen's 2.1. So all the electrons tend to hang out with oxygen. And so this ends up to be a slightly negative charge, while the hydrogens tend to be slightly positive. And so it can act like a tiny little magnet. Now when I draw carbon dioxide, carbon with my 2 double bonds, okay, oxygen has the higher electronegativity value, so they hang out with oxygen more. So this would be my slightly positive, and then this is my slightly negative. But shape also plays a role in polarity, and you can see that I can't really cut this molecule in half where I have a positive end and a negative end. Hydrochloric acid. Okay, that's what it looks like. Chlorine is right next to fluorine, very high electronegativity value. So then here's my slightly positive, and this is my slightly negative. So another table just showing polarity and how things that tend to be polar have higher boiling points than those that are nonpolar or less polar. So I have a short video that I will play.
Dipoles cause polar molecules to be attracted to one another. Although the forces involved are relatively weak and short range, they can still have important effects on the properties of many materials. Bromine fluoride is a polar covalent bonded molecule. The slightly charged ends of the bromine fluoride molecule attract the oppositely charged ends of other polar molecules. Because liquid bromine fluoride has these dipole-dipole interactions locking the molecules together, it has a relatively high boiling point. As the liquid heats up, the molecular vibrations become stronger and the dipole-dipole interactions become harder to maintain. Eventually, the bromine fluoride boils. Similar liquids without dipole-dipole interactions will boil at a much lower temperature. Molecular fluorine, for example, which is completely nonpolar, boils at negative 188 degrees Celsius. Without dipole-dipole interactions, the molecules can separate easily.
Okay, the second type of IM force, intermolecular force, is induced dipole. And this is a polar molecule interacting with a nonpolar molecule by temporarily attracting its electrons. So in summary, here I have oxygen, okay, and you can see that it's nonpolar because they're both oxygen and they're sharing the electrons equally. But sometimes that oxygen gas molecule will interact with other molecules, like a polar molecule, in this case, water. And because we do have this polarity, a negative end and a positive end, this negative end will attract or cause a induced dipole. Because this is negative, well, that's going to push that electron away. So now the electron is hanging out over here, the ones that are being shared, and then as a result, this has a slightly positive. And so now we have this induced dipole attraction. So if I had to summarize induced dipole, it'd be a polar molecule interacting with a nonpolar molecule. Oh, and I think I got another video there.
The oxygen dissolved in water is vital to the fish and other aquatic organisms. But how does a nonpolar molecule like oxygen stay dissolved in a polar solvent like water? Let's take a closer look. The positive pole of a water molecule causes a temporary change in the electron distribution of an oxygen molecule. The oxygen molecule now has a dipole, with the negative portion of the oxygen dipole facing the positive pole of the water molecule. Dipole-dipole interactions allow the nonpolar oxygen molecule to be weakly attracted to the polar water molecule and remain in solution.
Okay, the third type of intermolecular force is hydrogen bonding, and this is a type of dipole-dipole force. And basically, this involves a hydrogen atom and another highly electronegativity atom. So something with a very high electronegativity value, like oxygen, nitrogen, fluorine. But we show dotted lines to indicate those hydrogen bonds. So you can see that each one of these little water molecules, there's hydrogen bonds taking place. And this is why water has such a high boiling point, and because they act like little magnets. When you heat up water, they start to vibrate, and it takes a lot of energy to disrupt those hydrogen bonds, so that way water can escape as a liquid to a gas. Hydrogen bonds play an important role in life. We talked about this in biology way back in chapter 2, sophomore year, how water, because of these hydrogen bonds, water has a high specific heat value. We can use it as an insulator. This is the reason why when we go outside, we don't evaporate in the sun, because we have hydrogen bonds, so as a result, higher boiling points. And hydrogen bonds actually hold our DNA together, and I'm going to show you on the next slide here. Now, this bond is weak, but because there's hydrogen can be abundant, when you have a lot of them, it's a very, very strong bonding. So, yeah. So here's my DNA structure, okay? And remember, DNA is like a double helix, right? This is the side of my helix, my sugar phosphate. So it's phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar. And this is a nucleotide, in this case A, and this is T. A always pairs with T, C always pairs with G. And you can see these dashed lines. And this is thymine bonded to adenine, but it's literally held together by hydrogen bonds. Okay? So when DNA wants to unzip, what's happening is that we have enzymes that are disrupting this hydrogen bond, or when we do a PCR analysis, what we're doing is we need to anneal DNA, I think is what it's called, and what we do that just by heating it up, and we disrupt those hydrogen bonds, so that way we can create more DNA in the PCR and amplify the DNA sample. The fourth and final IM force is London dispersion forces, and this is strictly between noble gases and nonpolar molecules, things that are very inert, or do not attract others. And what's happening here is we have two nonpolar molecules like iodine gas, and electrons, they're being shared equally, but sometimes those electrons that are being shared just kind of end up on one of the atoms just spontaneously, and so as a result you end up with this slightly uneven electron distribution, or a temporary dipole. And so that is an example of London dispersion.
In any atom, the random motion of electrons around the nucleus can create a positive pole in one part of the atom and a negative pole in another part. If another atom is located nearby, the temporary dipole can induce a dipole in it as well. The two atoms are held together for an instant by the weak attraction between the temporary dipoles, before separating again as electron motion causes the dipoles to disappear.
Okay, so that is it, I think, for my lecture on intermolecular forces. And so I talked about 4 of them: dipole, dipole, hydrogen bond, induced dipole, and London dispersion. And then just know that the stronger forces like dipole, dipole, hydrogen bonds tend to have extremely high melting points and boiling points. So that does it.